Hello everyone, welcome back to Alkaline Hydroxide 784, and today in the physics series we are covering the gravitational field. Um, yeah, so in the gravitational field we are gonna talk about many things. And there's a bunch of topics in physics which have pretty similar, like certain similarities in what you're being asked for, like the force, potential, that kind of thing. So yeah, this is the first one. And it's about gravity. And I think the interesting thing about this topic is the space stuff because you can imagine planets orbiting around each other and doing things, and you realize that all of it is because of gravity, and it's just wow. Okay, I mean that's the only way to make yourself be excited about this topic. Unlike quantum physics, it's just way more exciting. Okay, I'm just kidding. Okay, let's move on. So in the gravitational field, there's a bunch of learning outcomes, so I'm just gonna follow that, or maybe attempt to follow it, I guess, and we'll see how we go about it. So the first one is about what a gravitational field is. Okay, so um like you think about the word gravitational field and you're like, huh? A field? Why is it a field? Like the first thing that comes to your mind is a grass field, or I don't know, some other kind of field. Is there really any other kind of field? I don't know. I mean, in that a thing that's actually visible. But a gravitational field is invisible. You can't really see it unless you know how to see forces. Is that a thing? Maybe you can. Like if you're a machine or something, you can probably see it. But it is a field of force. So it's, you imagine it like this, you know, you know your vectors, you have like a space that you put your vectors in. So imagine this like that space. Like the space is just full of forces in moving in different ways and everything. And or if you wanna think like Einstein, you can think about it like that stretchy thing with when you put a planet in it, it makes like a depression into it. Yeah, you can think like that also. I don't know. That's up to you to decide. So so the idea is that gravitational field is a force field, like a field of force. And all the objects in that field affect it in many ways. They deform the field in certain ways. They exert forces in different directions, and many different things happen because of that. So the next thing that we need to know is what exactly is the strength of the field at any point. So what's the gravitational field strength at the point? Basically, if you think about it, if you don't think about the object per se, you just think about it in the strength of the field at that point would be whatever force that you get at that point per unit mass. So what this means is if you keep like 1 kg mass at that particular point, okay, maybe not 1 kg, 1 gram would make more sense. A 1 gram mass at that point, and you see how much force is being exerted on the mass by the field because of the influence of other objects or anything else, that there might be a force being exerted on the mass, and that force is the gravitational force in this scenario. I mean, in this topic you're talking about gravity, so how much gravity is being exerted on the mass, and when you divide the force by the 1 gram, you get your gravitational field strength. But since we are using SI units, you should look at it in terms of kg. So in this scenario, the force over 1000 of a kg would be your answer. And that is the gravitational field strength. So in for Earth, we have the gravitational field strength of 9.81 at very close distances to Earth, because the further you go, the more different it will be. So let's say if you are standing on the floor or sitting on a chair or doing whatever it is, the force exerted on you is 9.81 per kg, in a way, like Newton, yeah, 9.81 meter per second square or Newton per kg. So that many newtons is acting on you at the moment. And that's why when you calculate weight, you always times the mass of the object by 9.81 to get the force of weight, I guess. So that's just gravitational force. Okay, so now let's move on. Okay, what's this? Recognize the analogy between certain qualitative and quantitative aspects of gravitational and electric fields. Yeah, this is what I was talking about. There's like more than one topic related to forces in this case. Okay, I'll just quickly, briefly tell you about it. I think I might talk about it in more detail for the electric one later on. But the idea is that in a gravitational field you have a force, and electric field also have a force. But the force is caused by a different thing. Like in gravitational field, it's caused by the mass of the object, versus in the electric field is caused by the electric charges on the object and things like that basically. So that's one of the analogies that you can get. The other analogy was that the the field strength, I guess, is the same logic. It's like force per unit something. In gravitational field is per unit mass. In electric field is per unit charge. And so on and so forth. It's like you replace all the mass with the charge and you kind of get a similar equation for both in terms of the two different topics. And maybe I might explain on this more when we get to electric field, because technically by then you should already be well aware of how gravitational field works, and this would make more sense in that topic. So yeah, so the next point is Newton's law of gravitation. So what is the Newton's law of gravitation? The Newton's law of gravitation states that the force between two objects is the product of the masses of the two objects over the square of the way that is actually written is the Newton's law of gravitation is states that the force exerted the force between two objects is between two objects the force that one object exerts on the other and vice versa is proportional to the product of the two objects and inversely proportional to the square of the distance between the two objects. Yeah, as you can see, the terminology used is pretty important, so yeah, please look at your notes for the right terminology. I may know what it means, but I may not say it the right way, so I think this is as right as I can say it. This is as correct as I can get. So just use your proportional, that makes more sense. Proportional and inversely proportional. Yeah, so what does that mean in equation form, because you can't understand that whole bunch of words? Well, it just means that F is equals to big G times mass 1 times mass 2 over r squared. That's a lot simpler to say, I guess. So the reason why we have to say proportional is because of the G, because otherwise it would be equal to, kind of, in a way. So so the G is like a constant of proportionality, and you can find it in your data booklet, so I don't want to talk too much about it. I think it's like 6.67 times 10 to the power of negative 11 or something like that. I don't know. Just check your not booklet, the data sheet, like that list of data. Just use that if you forget the value, like I do. Yeah, that's not the most important thing here. The important thing is the rest of the terms. So imagine you have like two big balls or something. That's because it's easier to do this with uniform shapes. So use two big spheres, and one of them has a mass of m1 and the other has a mass of m2. The distance between them is r, and this is how you get the force between each of them. So this is equal to the force that at the first sphere exerts on the other, and it's equal to the force that the second sphere exerts on the first. So yeah, it's the same force, it's just that it's in two different directions. The attractive forces, so the first sphere would be attracting the second sphere towards it, the second sphere in turn is attracting the first sphere towards it, and that's how the force works in this case. Okay, so now let's move on to the next thing that we have to define, which is the gravitational field strength. So as you heard earlier, it is equals to the force per unit mass, right? And you know what is the force now? It is gmm over r squared. So how do you get gravitational field strength? Good question. You just divide it by m. For which m, you ask? Um, Good question. You divide it by the m of the thing that you're looking at. Like, so the point mass would be the smaller object. So you don't, in this scenario, you don't actually need to take note of the mass of the object per se. You only need to include the mass of the bigger object which is attracting the smaller object. So the in this case, the formula for G, which is big G, big M over R square, the big M is referring to the big object that is attracting the point mass. Yeah, that's how you think about it. So in this scenario, the point mass is like, you imagine like this infinitesimally tiny little thing that is very small. Or it could be a 1 gram mass also, I don't know. But you have to divide it by 1 gram. But in this case, you imagine it as a really small thing that the object can act on, in the sense. So your big M, maybe for example, if you're looking at Earth, this is how you get your 9.81. You put G times the mass of Earth over the radius of the Earth, because you imagine it as someone standing on the surface. And that's how you calculate your gravitational field strength, aka your small g. Right. And then now that you know the equation of gravitational field strength, you can then find the gravitational field strength of anything, like of anything that you want for point mass, in the sense. Okay, but point mass means like you imagine it as a sphere, so it has a point in the center, and you understand why they use this later on, as I mentioned when I explain how it works. Actually, they don't have it here, do they? Do they have that point here? Never mind. I'll explain to you once you're done explaining how these formulas work. Okay, so yeah, that's what the point mass is related to. And the unit mass is the one with the 1 gram thing. Sorry, just in case I confused you just now. So the point mass is the one with the mass big M, and the unit mass is the one which is not even stated in this gravitational field strength formula, because we so-called divided it out. Okay, so now you can use this formula to find any gravitational field strength in your question. You can try to find the field strength of Mars, for example. And yeah, you can just use it to solve your questions. I hope you should be able to do that without being confused. Right. So yeah, so before I move on, I'll just explain to you what it means to have a point mass. So there's this theory that they use where I'm sorry. There's this theory where you imagine everything as a perfect sphere, because we are usually dealing with planets here, so yeah. And if you imagine the force in terms of the R, you're looking at it from the center of the sphere, not from the outside. So in this scenario, you imagine the sphere is consisting of many covers, like little balls that they can open up, like many layers, like an onion. And the center is where you calculate the R from, right? So what this means is like you imagine the outer layers as hollow layers. Like if you take away what's inside, there's just a hollow layer, and therefore it doesn't really have so-called mass or force, like ability to exert force. And as you keep going and going, you condense all of your so-called force into the center of the thing. And that's why we use the radius from the center of the sphere per se. And that's why they're called point masses, because you're considering the point at the center of the sphere. So yeah, that's what it means. That's all. That's all I have to say. I don't know if you're supposed to explain this because it's not even written here, so I don't know. You might need to explain it. I'm not sure. So that's the logic, I think, that they use. So now let's move on to stuff that the thing that I mentioned at the beginning, which is that the G here is about 9.81, and as long as you are nearby the Earth's surface. And the reason why they say that is because it doesn't deviate that much. Like if you change the R like that by like little bit, because the radius of the Earth is so big that for any small increase in that R, you're not gonna get much difference in the value of G. It's usually rounded off, and then you can't even notice that there's a difference. And therefore, you can just use 9.81 without a care in the world because we like to idealize things. Okay, anyways. So then the other thing that we should take note is that g is equals to the acceleration of free fall, and what that means is if in the absence of things like friction, air resistance, anything else, if the only force acting is the gravitational force, the acceleration of the body is g 9.81 in terms of the Earth. It could be something else in terms of other bodies. So yeah, because the reason why the acceleration is called acceleration of free fall is because you're attracted to the Earth, and when you're attracted to the Earth and you're not on the surface, you're gonna be moving towards the surface, and that's basically falling down towards the Earth. So that's why it's the acceleration of free fall, in a way. Okay, so yeah. So now let's move on. Define the gravitational potential at a point. Right. Okay, why did I say it like that? That was so weird. Okay, never mind. So what's the gravitational potential at a point? You heard of potential energy? So this is just potential. So that means it just means the work done per unit mass in bringing a small test mass from infinity to that point. This is the actual definition you're supposed to write, so just remember this and write. Yeah, it's written in your syllabus itself, so just if in case you lose your notes or something, look at your syllabus. At least you'll get something there, some kind of definition. So, why does it mean this? The potential is kind of like the how should I say it? It's like the potential energy per mass. It's like when you find the dE or dm kind of thing. So you're dividing it by the mass. That's what it's defined as. It's just how it works. Like you don't really have a natural thing that we can call potential, but we just define it like that. Yeah. So basically what it means is if you spend a certain amount of energy, aka you do work, to bring a small test mass from infinity to a certain point, what does that mean? Imagine you have like this big godlike hand holding that test mass, like a unit mass, maybe like a small little thing, and it's moving and it's preventing it from is make allowing it to move down slowly from infinity to the point. And you already realize that the gravitational force is attractive, so you're realizing that you don't really need to do work to bring something from infinity to the point because it's going to be attracted on its own. But so the work done here is actually against the attraction. So when you're trying to support the object, you're preventing it from moving, right? So the work done is actually negative, and that's why your gravitational potential is negative. So, but what's the point of having a potential? Why do you need it? Can't you just have the energy? Well, the reason for this is because if you remove the mass from the equation, then you have this constant value that you can literally apply to any mass. So it's like doing MGH in the sense, your MGH, you can use it for any mass and any height here. And that's only because you're near the Earth lah. But if you're very far away from the Earth, you can't really use MGH because your G won't be the same anymore. So this is more like the integrated version of G, like over the H in the sense. And actually that's what it is. It's just the if you integrate g with respect to h, that's what you get. You get potential. So, and that's why potential is actually negative g m over r. It's not r squared but r, because you integrated it once by r, and therefore you have a bigger power per se. Instead of -2, you have -1. So that's the equation of potential, and your potential just looks like this circle with a stick poke right to it, like your, I don't know, your satay stick. Imagine you poke it through the stuff on your satay. I don't know. Yeah, you get the idea. That's what it looks like. So that's the equation, and just use it to answer your questions. If they ask you for potential, that's how you answer it. Yeah, use the equation. Right, so the next point is circular orbits. Right, so inverse square law fields, blah blah blah. Well, I can't believe they referred to the field as inverse square law fields. How brilliant. Okay, the reason why they put inverse square law is the if you realize just now, the the force is over r squared, so yeah, inverse square. That's just pretty much it. It's proportional to 1 over r squared. That's the logic of inverse square law. It's as simple as that. So let's say if an object is maybe 2 meters away, the force is F. So if the object is now 4 meters away and there's nothing else that's changed, the force is now what? So it's double the distance, but it's 1/4 the force. So that's all you need to know for the inverse square law. Just use that logic when you answer questions related to that. And the question will usually be something like this, the difference between this and this. And it's usually they'll ask you an MCQ, because this isn't worth asking in anything else apart from MCQ. So yeah. So now let's move on to the important thing, which is what we actually covered in the last topic, circular orbits, but we apply it to gravitational force in a sense. So but in what scenario do you see this? Well, you see it in satellites or planets or anything that's orbiting around another bigger body in a sense. And the reason why I say orbit is because that's what is literally said here, circular orbit. And usually orbits are the things that involve gravitational force. So let's say you have a satellite going around planet Earth. What's the force acting on the satellite? The gravitational force, most likely. More than anything else is the gravitational force. And this gravitational force is also its centripetal force, because it is directed towards the center of its orbit, which is obviously the center point of Earth. And as you can see, the satellite doesn't fall towards Earth, so the gravitational force is enough to make it go around and around and around without falling down. But at a certain point of time, it will not be enough to sustain this, and the satellite will eventually fall down and burn up in the atmosphere before it even reaches the Earth. And that one is because of that is because over time there's still going to be friction, there's still going to be heat loss, like thermal energy will dissipate out, and therefore the gravity the gravitational force will decrease as the satellite moves down. The friction will make it move down and down, and at a certain point of time it will go so low that it ends up burning up in the atmosphere. Yeah, that's what happens. The atmosphere is huge, and sometimes it doesn't have enough force all of a sudden, and it just falls free straight to the atmosphere. And that's where it ends up burning up in the atmosphere, because of the high speeds of the caused by the gravitational attraction in a sense. Right, so so when you do questions related to this, you just need to put gmm over r squared equals to mv squared over r, or whatever formula that you like to use. So you use this, and then you can remove all the r, because the r will be the same here, and you would then get gmm over r equals to mv squared, and then you can remove on the m as well, the small m in the sense. So g big M over r equals to v squared, and from there you can then simplify you can then find out the v square in the sense if you use your Earth's um you know if you use your Earth values, you can then get um the speed of escape, the speed that you need to, in order to escape Earth's velocity, Earth's atmosphere, which is about 11 kilometers or something. Wait, no, not 11 kilometers. That's not, that's too little. 1100 kilometers per hour, I believe. I'm not sure. 1000 or even, okay, actually don't remember the exact power of it, but it's about 1.12 times 10 to the power 5 or something. I'm not sure. Just find it yourself. It's very easy to calculate. It's not important right now. So you can use, you also you might have to answer this in the question. So just use this to find the speed that it would take to escape the atmosphere. And finally, the last point, which is understanding of geostationary orbits and their application. Um, so this is once again related to stuff like satellites and things like that, because um, yeah, it's just about different kinds of satellites and the advantages and disadvantages of each satellite. As you can see, I do not remember that information because it's really just some information that you might have to remember. I do know there's one that's 24 hours, so sorry, not 24 hours, as in, sorry, wait. Yeah, its orbit is 24 hours long, and yeah, and there's another one that's, and since the orbit is 24 hours long, it is always monitoring the exact same spot if it's moving along with the rotation of the Earth. So that's one of the satellites. And then there's another one that's further away, there's another one that's nearer and all that stuff. So look at your school notes for this. If your school notes doesn't have information, then go and pester the people from other schools to lend you the notes so I can look at it. There might be something tested on this, so just read it up in case you haven't done so yet. I mean, the physics paper has already, like one of the physics papers would have ended or not? Maybe, I don't know. Yeah, ended already. So there's still some more papers. So I think you can still have some time to revise it before that paper. So yeah, good luck for your physics exams, I guess. Anyways, yeah, I think I know there's a lot more complicated stuff that we can talk about here because the questions are actually way more can be quite complicated compared to whatever we see here in the learning objectives. Because I do remember that we learned more stuff than in the learning objectives because like the that the thing about the spheres opening up one by one like a Matryoshka doll or something. Yeah, that kind of that theory that I told you earlier and things like that. But I think this should be okay enough information for when you're revising because you should already know the other extra information that you learned in school or you gain from answering those gravitational field questions. So I hope that you have that you found this video useful or like useful for revising. And actually at first I found this topic very hard. Like honestly, I was like very confused by this topic. For once I saw that it was just memorizing a bunch of equations and applying them accordingly, it became so much easier to do the topic. So just think of it in that sense, like just think of it as a topic where you apply a variety of equations according to what the question asks for. So the important thing is to read the question properly and also use your calculator correctly so that you don't make careless mistakes in it. Yes, once again, if you found it useful, you can press the like button and subscribe. And with that, I would like to say thank you and bye!